Hi, I'm Awadh Bihari Narayan. Lohani sir have invited me to deliver a few lectures on SAR interferometry. Sir have already taught you something about SAR imageries, so I will directly come to the topic and briefly explain its working principle. It's just an introductory lecture to introduce you in SAR. In this presentation slide, we will start with information contained in SAR imageries, and then we will understand principle of in SAR, and then we will try to understand two most popular geodetic application of INSAR: DEM generation and deformation. SAR imageries are a two-dimensional array, and each pixel having a unique location in azimuth and slant range imaging plane. For interferometric application, we use a single loop complex product of SAR satellite, and more specifically, we call it SLC image. Each pixel corresponds to a resolution cell on ground, and the value stored in the pixel is a complex value. The amplitude of complex value is proportional to the backscattered energy from resolution cell, and phase, which is most important part, the phase value is proportional to the distance between satellite and the resolution cell. Now this is an area of our interest, and SAR satellite acquires imageries regularly. Suppose a satellite illuminates a resolution cell of this area, so the pixel corresponding to this resolution cell in the acquired SLC image will contain the backscattered complex reflectivity from this resolution cell, and the phase value will be proportional to the distance r between satellite and resolution cell. After first acquisition, satellite move around the Earth and comes exactly at same position to acquire SLC image of this area. Meanwhile, a land subsidence occurred and resolution cell moved d distance in the direction of line of sight. So now the phase value of corresponding pixel in the SLC image will be proportional to the current distance between satellite and resolution cell, which is r plus d. So if I will take difference of phase value of the SLC images, I can get a phase value proportional to deformation. The phase difference of two SLC images is called interferogram, but as in the SLC images, phase value is present as an argument of complex value. So the phase of the cross product of the complex reflectivity of one image to the complex conjugate of the reflectivity of another image will give us an interferogram. As images are acquired at different time, so atmospheric condition would be different while acquiring the SLC images. So in interferogram, an atmospheric phase component would be present along with deformation. And noise is a godlike entity you will find in every observation, in every experiment. So I have kept a separate presentation slide on noise. But it's an hypothetical case that satellite will move around the Earth and it will come exactly at same location. In reality, there would be separation between the positions of satellite while different visit for the image acquisition of same area. And because of this separation, which is called baseline, and this one B perpendicular is called perpendicular baseline. If you will draw a perpendicular from master satellite to the line of sight of slave satellite, it is called perpendicular baseline. So because of this separation, B, two more phase component arises. First component is due to topographic phase variation, and it is proportional to the height of the resolution cell. It is called topographic phase component. Second one is independent of topography. It is due to the flat earth, and it is proportional to slant range of the resolution cell and called flat earth phase component. Kt and Kf is kind of proportionality constant and can be written as follows, where lambda is wavelength, r is slant range, and theta is incidence angle. The flat earth component can be written as function of parallel baseline represented as B parallel. Each satellite has onboard GPS which provide us orbit location while acquisition of image. So by using orbit parameter, flat earth phase component can be simulated and removed from the interferogram. After removing contribution of flat earth component from interferometric phase, the remaining major phase components are corresponding to deformation, atmosphere, and topography of earth and noise. Two major geodetic applications of SAR is DEM, digital elevation model generation, and deformation monitoring. Digital elevation model gives us height of any location of Earth's surface, and deformation monitoring includes surface deformation due to earthquake, volcano, or groundwater subsidence, structural deformation like bridge deformation, and thermal expansion of building, etc. But in this one equation, only interferometric phase is known and all other phase component is unknown, including height of the resolution cell. Now one equation and four unknowns, it's impossible to estimate height h. So to estimate h, one thing can be done. If anyhow we can reduce these nuisance phase component and phase noise, it would be nice. So if the time difference between acquisition is very small, let's say assume image are acquired at same time or at difference of very short time gap, then the deformation will be zero, because deformation is a slow process except in case of earthquake and volcano. And atmospheric condition would also be the same for both SLC image. So atmospheric phase component will also be very small, and temporal decorrelation will also decrease, which is a large component of phase noise. So phase noise will also reduce. About noise and decorrelation we will discuss in separate lecture. So overall, all the phase components other than topographic phase component will nearly negligible. So now we can estimate height from this equation. Now we'll see a strategy for deformation monitoring. So in this application, our purpose is to estimate deformation of the resolution cell. Again, one equation and four unknown, in which component of my concern is deformation and other phase component like atmospheric phase component, topographic phase component, noise are nuisance phase component. Suppose for this resolution cell, if I want to estimate deformation between today and the day after 1 month, so I have to download SAR SLC image of today and that day, but there is no guarantee that atmosphere will be same for both images, so we can't remove atmospheric phase component. But something can be done with topographic phase component. We can reduce it by choosing SLC image which have very small baseline. If baseline will be a small, topographic phase component will also be a small. But this strategy would not be sufficient to remove its impact completely. But 1 minute. B perpendicular is known from orbit file, and KT proportionality constant can be estimated from metadata. If anyhow I will have this height information of resolution cell, I can remove topographic phase component completely. And from where we will get this height information? Digital elevation model. There are many digital elevation model available like SRTM DEM, STER-DEM, Cartosat DEM, and many more. But digital elevation model have some error which is of two types. As you can see in this figure that the blue line represents actual surface and the upper line in black represents the surface constructed by DM. There is two types of error. The first one is bias between actual and the DM surface. It's a spatially correlated or a spatially low pass in nature. And the second type of error is random error, which is spatially uncorrelated or high pass in nature. When we will simulate the topographic phase component, which is represented by this cap on phi topo, it will contain some error due to a spatially correlated and a spatially uncorrelated DEM error. When we will subtract the simulated topographic phase component to the interferometric phase, it will not remove topographic phase component completely. And in interferogram, with the deformation and atmospheric phase component, some residual topographic phase component will also be present. The present residual topographic phase due to a spatially correlated DEM error is called spatially correlated topographic error and represented by phi SCTE. And topographic phase error due to spatially uncorrelated DEM error is called a spatially uncorrelated topographic error and represented by phi SUTE. The subscript SC and SU stand for spatially correlated and spatially uncorrelated. And the TE in this subscript represents topographic error. After removing the contribution of known topographic from the interferometric phase, the resultant interferogram is called differential interferogram and the procedure is called differential INSAR. In short, D-INSAR. So let's summarize the procedure of deformation estimation. We had two SLC images. We did Hermite product of one image to complex conjugate of another image. We get a complex interferogram. Then we applied flattening to remove flat earth phase component, and then we simulated topographic phase component and subtracted to the interferogram, and then we extract phase from complex interferogram and we get wrapped interferometric phase which contains deformation, atmospheric phase component, a spatially correlated topographic error, a spatially uncorrelated topographic error, and phase noise. For the time being, just remember this word wrapped. We will discuss it in next lecture. Now I want to know how these phase components behave spatially. First of all, deformation. If a building is under subsidence, nearby building will also be under subsidence. So deformation is a spatially correlated or a spatially low pass in nature. For the range of kilometers, atmosphere doesn't change. So in the neighboring pixel, atmospheric phase component will not vary too much, and thus this one also a spatially low pass. And we already know a spatially correlated topographic error is a spatially low pass in nature, but the spatially uncorrelated topographic error and noise are spatially random or high pass in nature. But our objective is to estimate deformation only. So by low pass filtering, we can separate noise and SUTA, especially uncorrelated topographic error. But still atmospheric phase component and a spatially correlated topographic phase component is present along with deformation, and this is the limitation of D-INSAR. In the next presentation, we will discuss about different contributors of noise and decorrelation, and we will understand phase unwrapping, the most important issue of interferometry.